Another part of task 2 is related to load flow analysis. We have a 5-bus power system. The data are available in tables, and bus generator 1 is considered as a slack bus, swing bus. Bus 3 is a voltage control bus, PV bus, and bus 2, 4, and 5 are load buses. So the task asks us to calculate the Y bus, admittance bus, and then voltage of bus 2 and 3 by iterative method and reactive power at bus 3. You have access to the formula as well. So in order to calculate, just some review about the Y admittance, how we calculate the Y admittance. We know that the node equation, if you have, for example, a bus with a power system with 4 buses, you have a matrix with a dimension 4. And we know that this diagonal parameters elements equal to sum of the admittance directly connected to that point. And the off-diagonal element, for example, these or these, equal to negative of net element, net admittance connected to bus I and J. For example, for this power system, the Y bus, the admittance bus, can be calculated in this way. For example, for bus 1, this array will be sum of all admittance connected to bus 1. On bus 1, we have 3 branches are connected to bus 1. YC plus YD plus YF. However, the array Y1, 2, this array is negative of the admittance connected between bus 1 and bus 2. That's why it is minus YD. It was the background. And with this input, we have Y bus with dimension 5. And according to this power system, some array are 0 because there is no connection between them. For example, this one, array Y1, 2 is 0 since bus 1 and bus 2, there is no direct connection between them. So other 0 as well, since there is no branches between them, there are 0. But we have other arrays. We will start from the diagonal arrays. Started from Y11, it's the sum of all admittances connected to bus 1. The bus 1 is connected to bus 5 here with a transformer. And we know that this transformer data, the resistance and the impedance can be calculated, can be obtained from this table between bus 1 and bus 5. What's the R and the X? The admittance is 1 over impedance, R plus JX. Then we can calculate in per unit. Y22, this bus, is sum of all admittance connected to to bus 2. So we have this admittance here, here. There are transmission line. This one, impedance Y over impedance of this line between bus 2 and bus 4. This one is related to admittance between bus 2 and bus 5. And according to this table, we have B as well, susceptance. It means that we have capacitor here, or we have capacitor here as well. So we know that this capacitance, admittance, G plus JB. So admittance, we don't have real part, just the imaginary part. The admittance, we know that this is B, the half of B. The other half is here. B over 2. And this one, B24 divided to B25 is this one. Y33. This one is bus 3, and the only admittance connected to bus 3 is this transformer. And we can find the parameters here. This is the admittance of impedance of transformer. The admittance will be Y divided by the impedance. And Y44, all parameter are admittances connected to bus 4. The first item between bus 4 and bus 3, this one, the relay transmission line. Between bus 4 and bus 5, this transmission line. Between bus 4 and bus 2, this transmission line. And B, because we have capacitor here. We have capacitor here. And finally, the last diagonal array is Y55. You can see this 5 is connected to transformer, transmission line, and to capacitor. You can find the diagonal parameter in this way. Just to erase. Okay, so what are the off-diagonal parameters? You can see some of them are 0, but some of them are non-zero, and we have to calculate. For example, Y15, and we know that these are similar to 1, 5. So in order to calculate 1, 5, it is minus whole admittance connected between two buses. And we know that there are just one transformer between them, and the parameter are available from table 4. And admittance between bus 2 and 5. Bus 2 and 5. What's the admittance between them? There is one impedance here, but you have to remember that we have capacitor here, but this capacitor is connected to just bus 2. We have capacitor here, but it's only connected to bus 5. We don't consider. The only impedance or admittance connected to both of them, both 2 and 5. And then admittance array 4 and 5. Between 4 and 5, we have a transmission line. Between 2 and 4, 2 and 4, there is a transmission line. Between 3 and 4, we have a transformer. And the other are 0. In this way, we can finalize Y bus admittance. You have this matrix with dimension 5. If you fill with different array, it will be your final Y bus. Okay, the next question. Calculate the voltage at bus 2. We want to calculate this bus. And we have the formula based off the iterative method. We use this formula. For example, it's a general formula for voltage on bus 2. It will be 2. Y will be diagonal of the admittance bus Y22, the active and reactive power at bus 2, the voltage of bus 2, and the connection to the other buses. However, you have to know that for iterative method, we start with the initial value. Initial value of the voltage of bus 2 is 0. The voltage amplitude is 1, the angle is 0. But since it is voltage on bus 2, bus 1 is suppose that is calculated before. We start from bus 1, 2, 3, 4, and we will continue. So now we are calculating bus 2. Suppose that bus 1 is calculated before. So we have access to the voltage on bus 2 before. That's why we have 1 here. But for bus 2, voltage of bus 2 is initial value, bus 3 is initial value, and initial value. And if you use this formula, and this Y can be obtained from this matrix. And if you substitute different parameter here, for example, Y22, it's this one. And you substitute here. The active power and reactive power, you have to know that. You have to two loads, that is 8 is in per unit. Suppose that 100 megawatt as a base power, and you have to convert to the per unit these loads. Since they are loads, we consider negative, and they are mentioned here as well. It's the active and reactive power at bus 2, and this parameter can be calculated from, can be obtained from the Y matrix. And if you calculate them, you can see this one is the voltage with the initial value. And this final result will be the initial value for the next iteration. You can see here, instead of previously, we consider 1 with the angle 0 as a initial value for voltage of on bus 2. However, the next iteration, instead of 1 with angle 0, we use this result for the initial value of the voltage. And then the task asks us to calculate the reactive power. You have to know that the reactive power, you have the formula, and the angle of voltage bus and the admittance array will be used in the formula. And according to the bus admittance bus, you can substitute, and you can see for the first iteration, for bus 3, it's the voltage bus 3, the admittance can be calculated according to this one, voltage on bus 1 with the initial value. This angle, since it is started with initial value, the angle of the all buses are 0. That's why this one is 0, this one is 0, and this one is the angle of the admittance. You can see that's why we have minus this part. And if you fill the formula with the corresponding parameter, you can calculate the reactive power on bus 3. And the last part asks us to calculate the voltage angle at bus 3. So we have the formula. You can see this is the formula you have. You can pay attention that it's the initial guess for the amplitude of voltage. But V1 and V2, we use 1 instead of 0 because we calculated before. But for bus 4 and 5 that are not calculated yet, so we consider 0 initial value. And these are Y bus. And for the first iteration, if we substitute the parameter in this formula, you can calculate the whole voltage, the complex voltage. Just one thing you have to get the active and reactive power on bus 3. On bus 3, we have 2 loads, the active load and reactive loads. And according to this table, it is PV generator, active power can obtain from this table. However, the reactive power, we have a reactive power here, but from the previous calculation, we calculate the reactive power on bus 3. We use this calculation result here, 5.22 minus, because this is the load reactive power, that's we decrease the reactive power. For the first iteration, the voltage bus 3 is the initial value. Since it was the PV bus, we use the amplitude of voltage from this table. However, for the second iteration, this voltage is obtained from the previous iteration. We change the initial guess to increase the accuracy. In this way, we can calculate the complex voltage, and the angle of the voltage on bus 3 will be calculated. And the last part is related to Gauss-Seidel difference with the Newton-Raphson. And I will show you the different main step on Gauss-Seidel and then Newton-Raphson. We have a equation, and we want to find the root of this equation. This is the main goal. Suppose that in Gauss-Seidel, this one is the equation, nonlinear equation we want to solve. Based off the Gauss-Seidel, we can rewrite this nonlinear equation with this expression. It's the state variable, and we can write the state variable in terms of nonlinear function of the state variable. And we want to find what's x, and we have to write this equation but by non-iterative method based of this equation, the same things we did in the Gauss-Seidel. We started from the initial value, then we calculate x, and the calculated x will be substituted as the initial value in the next iteration. And the iteration ends until the following convergence criterion. You can see the difference between two results in two iterations will be very small. you can see in this figure, we will start from the x0. After one iteration, we goes to x1, and then second iteration, third, and will continue. When it will converge to the final result, the difference between the two iterations will be very small. And then we can say we reach a great result. However, in the Newton-Raphson, how to uh, how to play with the nonlinear function will be different. This is the nonlinear function equation, and you want to find what is x in this equation. In Newton-Raphson method, you use the Taylor expansion, and this is the Taylor expansion with unlimited terms of derivative. For example, you have a constant value, you have the second term is related to the first derivative of the function, the second derivative, and the other derivative. In the Newton-Raphson in load flow calculation, just only the first two terms are enough according to the experience we had in load flow analysis. The first term and the second term that is related to first derivative. And if you use just two terms, you can finalize the load flow based off the Newton-Raphson method, and it will be solved by the iterative method. And you can see what's the difference in the mathematical procedure between the Gauss-Seidel and Newton-Raphson.